All right, so we're going to start in on our next chapter, chapter 18. And we kind of already previewed the functional groups of this unit. Alcohols we spent a bunch of time talking about. The remaining ones are all lumped into this same chapter here. So ethers, epoxides, thiols, and sulfides. All right, and our focus for today is going to be on that first functional group, ethers, and we're going to start with where we normally start, which is how to name them. All right, so let's get our example down. So the one thing that we're going to keep in mind with ethers that are a little bit different from a lot of the other functional groups that we introduce is in the world of nomenclature, they are not treated as functional groups. They are treated as substituents. Kind of like how alkyl halides, that chloro group is a chloro substituent. It goes out front of the name. You don't end up changing the suffix on that parent chain. Same thing with our ethers here. So ethers are substituents in the world of nomenclature. All right, so something's going to sit in the front half of our name, not in the back half of our name. All right, so step one, we got to find and name our parent chain. But with ethers, we have these two alkyl groups on either side of our oxygen, right? Remember, by definition, an ether has an oxygen that's bonded to two different alkyl groups. All right, so when we figure out what our parent chain is, we're going to compare those two alkyl groups. The one with the longest continuous set of carbons, that becomes our parent chain. So for this here, I'm going to chop at my oxygen. I'm going to say, all right, it's either going to be this 3-carbon group here or this 2-carbon group here. Which one's going to be my parent chain in this molecule? The one on the left, the longer one, right? So again, like always, we're looking for that longest continuous set of carbons. All right, but it's going to be the larger, or rather longest continuous set of carbons. Larger of those two groups bonded to oxygen. All right, so in this case here, like we said, it was the one on the left in green here. Those 3 carbons is going to be my parent chain. Again, we're not doing anything to the back half of our name, so my parent chain here would simply be propane. All right, that means that this other chunk, my 2 carbons and my oxygen are going to be that ether substituent. All right, so step 2, we're going to find and name our substituents. We got a new type of substituent here, our ether substituent. How do we go about naming those? We're going to use that number of carbon prefix plus the ending. We have a special ending for these ether substituents, oxy. So 2 carbons, I would use what prefix? F. And then I'm going to use this new, not ethyl, but since it's a ether substituent, this is an ethoxy substituent. All right, then we number our parent chain, and then finally assemble everything together. and nothing new to add there. So I'm going to number my parent chain. Again, I want my substituents to be on the lowest possible number. So that's going to be on carbon 1. So this would be 1-ethoxy propane, all one word. All right, let's do 2 more examples here. I want everybody to take a minute and name these molecules for me, these ethers. All right, let's look at this one here. I'm going to chop it at this oxygen, and I'm going to look on either side. Which side is my parent chain, the left or the right? Right. Right, I got that longer set of carbons. All right, my longest continuous set of carbons. So my parent chain here is going to be a butane. And then I'm going to look, I have this normal alkyl substituent here, a methyl group. Remember, alkyl substituents get that YL ending. But I also now have one of these ether substituents. What would we call this 3-carbon ether substituent? Propoxy. A propoxy group. So prop, meaning my 3 carbons, and oxy being that ending I use for my ether substituents. Then I'm going to number my parent chain. There's nothing special about this substituent here. It's not treated with any sort of priority like it would be if it was a functional group, but I still want the lowest possible number in my name. So that means I'm going to put that propoxy group on carbon 1, that methyl group on carbon 3, and just like always, I'm going to arrange these in alphabetical order when I build my name. So 3-methyl, 1-propoxy butane. All right, what about in this molecule over here? Which side is my parent chain? Chop at that oxygen, the left or the right? Left. The left-hand side. How many carbons are in that parent chain? 6. Awesome. Okay, a lot of people are very tempted to always want to put that ether group on carbon 1. No. You still need to find your longest continuous set of carbons, which are these 6 here. All right, your ether substituent does not always have to be on carbon 1. In this case, it is on carbon 3 in my hexane parent chain here. All right, and since this is a 1-carbon ether substituent, we would call it a methoxy group. So this would be 3-methoxyhexane. Cool. All right, so again, ethers in our nomenclature, they're treated as substituents. They go out front of our name. We got to find our parent chain, whichever one of those alkyl groups it has our longest continuous set of carbons, and then the other part becomes our ether substituent. All right, and what we learned how to do here was to do our systematic naming by applying the IUPAC rules. All right, the IUPAC is that International Union of Physical and Applied Chemistry. They are the group that comes up with all of our nomenclature rules. So anytime that we're talking about nomenclature and we're applying these rules, we're doing our parent chain, find and name our substituents, number, assemble everything together, those are always the IUPAC naming rules. All right, ethers are used very often in organic chemistry as solvents, and you see the same ones over and over and over again, all right? So instead of referring to them by their systematic names, their IUPAC names, there are a bunch of them where we instead have just simple common names for instead. Whoa. Right? So for example, if I took this same ether here and I wanted to name it just using its common name, what we're going to do is name each of our alkyl groups that are bonded to the oxygen. So I'm going to look on either side of my oxygen here. This 3-carbon group would be a propyl group. This 2-carbon group would be an ethyl group. And we're just going to assemble those in alphabetical order, followed by the word ether. Assemble in alpha order. Followed by that word ether. So this one here would be ethyl space propyl space ether. That would be our common name for our ether here. Just name each alkyl group followed by the word ether. Importantly, this doesn't work for all ethers that we could think of. In fact, the example that we came up with over here with our branch point, we couldn't do this common name scheme for. But for very simple ethers, we can just refer to them by their common names. All right, so let's just practice this a little bit. I asked you for the IUPAC name before. Now I want the common name of these. So this one here has one 4-carbon group on the left, a butyl group, and then a 1-carbon group on the right, a methyl group. So we put those in alphabetical order: butyl, methyl, ether. Our next example, we have this 2-carbon group on the left and a 2-carbon group on the right. So an ethyl group over here and an ethyl group over here. Rather than saying ethyl, ethyl, ether, what do we think we're going to do? Diethyl ether. All right, and this one here is actually quite special. In fact, if you encounter any ether in your lab, I can almost guarantee you it would be diethyl ether. All right, this is a very commonly used ether used as a solvent. Right, we talked about these ethers as being fairly non-polar. They got a tiny bit of polarity because of that oxygen in there, but generally speaking are not a strongly polar group. They also have a really low boiling point, which is great for when you're doing chemistry. You do a reaction and then you're trying to get rid of that solvent to leave behind your product. So ethers are very commonly used as solvents, diethyl ether in particular. So common, in fact, that if you ever read a protocol and it says something like dissolve your substrate in ether, just straight up the word ether, it's specifically referring to diethyl ether. All right, this one is so common that it gets that name of that full functional group. You're reading your protocol and you're like, that's not a molecule, that's a friggin' functional group category. They use the word just straight up ether to refer to specifically diethyl ether. All right, so ether is very commonly used in the labs as solvent. Besides that, not very interesting functional groups. All right, we're going to learn a few reactions to make them, a few reactions to break them apart, actually just one reaction to break them apart, and that's about it. They're really not great starting points in any sort of an organic synthesis. Okay, so our first reaction that we're going to learn is how to make them. So this is an acid-catalyzed ether synthesis. All right, and it is a lot of analogy in the reactions that we covered last class period at the very end of our alcohols chapter. This is yet another reaction that is a dehydration of alcohols. All right, this reaction is often competing with the other dehydration reaction that we discussed. So let's just remind ourselves from chapter 17, we talked about how we can take alcohols and we can perform these dehydration reactions to produce, to create what products? So yeah, alkenes are what we get when we dehydrate an alcohol. We get those carbon-carbon double bonds. Remember, we had to talk about all those different, where the location of the double bond was going to be, what the stereochemistry of the double bond was going to be, right? We had those dehydration reactions that produced alkenes. And we also talked about how this had this like entropic control to it, where this reaction wouldn't happen unless you were at really high temperatures, where that entropy term would dominate. And that's really important here. We have to have really high temperatures in order to dehydrate our alcohols to our alkenes. All right, we're going to see a very similar reaction here where we can dehydrate our alcohol to our ether. And again, these are going to be in competition with one another. Meaning you'll always have a little of both going on at the same time. One way that you can kind of tune things a little bit more towards your ether product, if that's what you really wanted, is instead of cranking it up all the way to like 200 degrees Celsius, if we kept it at a more moderate temperature, we can try to favor that ether product, but again, we're always going to get a mix of both, right? They are always in competition with one another. All right, one more thing that we're going to note about this particular synthesis method. Yes, we can create an ether. We're always going to get a symmetric ether out of this. All right, by that I mean something like diethyl ether, where our two alkyl fragments are an exact match of one another. All right, so let's take a look at an example here. Let's do our chemical equation. We have an alcohol. All right, our conditions are very similar to what we saw before. We're again going to use this strong concentrated acid like sulfuric acid. Not sulfuric acid in water, but pure sulfuric acid or concentrated sulfuric acid. Truthfully, you never really get pure sulfuric acid because the second you open up that bottle, it absorbs some water from the atmosphere, but like 2% or something, right? So to say pure sulfuric acid is kind of a misnomer, but nonetheless, we don't really have water molecules floating around in there. We're going to see our sulfuric acid directly involved in our reaction. And again, this is going to create a symmetric ether. Because I started out with a 2-carbon alcohol, that's how I know I'm going to have these 2-carbon alkyl fragments in my ether. All right, now typically in organic chemistry, this is what we would do to sort of illustrate or summarize our reaction. But we're going to be good and we're going to do our balanced chemical equation here. So looking carefully, how many alcohol molecules do we think we're going to need to participate in this reaction in order to get this 4-carbon ether? We're going to need 2 of them. So we're going to have 2 alcohol molecules reacting with one another. And then the other thing that I need on my product side to get a balanced chemical equation, also hinting at the name of this reaction, a dehydration reaction, is a water molecule is going to be produced over here on the product side. All right, so in this reaction, you're going to have these 2 alcohols reacting with one another. All right, that'll form our ether product, and then our inorganic product, our water. Cool, all right. So, we're going to go and do our reaction mechanism. All right, but we're trying to get good at these reaction mechanisms, and we can reason our way through this particular mechanism if I just give you a few hints here. All right, so first of all, before we even dive in, we're going to take a step back and figure out what bonds on these reactant side we need to break and what new bonds on my product side we need to form in order for this reaction to occur. All right, so everybody take a second and take stock of what it is that we're going to be doing in our mechanism. What bonds are we breaking? What bonds are we forming in this mechanism? All right, who's got one? What's a bond that I'm going to have to break in my mechanism? I'm going to have to break an OH bond here. What else am I going to have to break in this mechanism? Yeah, so the carbon-oxygen bond. Right? And I'm going to tell you, one of these alcohols gets its carbon-oxygen bond broken. The other one, its oxygen-hydrogen bond broken. All right? This one, where we're going to be breaking the carbon-oxygen bond, this is the molecule that's going to play the role of the electrophile in my reaction. And the other one is going to play the role of the nucleophile in my reaction. All right, what new bonds are we forming in our mechanism here? We got a carbon-oxygen bond that we're going to need to form, right? That new bond in our ether. Whoops. And what else are we going to have to form here? Looking at my inorganic product. Oxygen-hydrogen bond. So this is what our mechanism should accomplish here. Breaking these bonds on our reactant side and forming these new bonds on our product side. Whenever you're going to sit down and try to do a mechanism, that's what you want to think of what needs to be accomplished. What bonds do I have to break? What new bonds do I have to form? All right, I'm going to be good, and we can note that this was, again, let's say moderate heat. Okay, and then I want to think about the conditions of this reaction. All right, what are the conditions of our reaction? Acidic or basic? Acidic. We have that strong sulfuric acid catalyst in there. So we should see this acidic conditions. Where we're going to make sure we have no strong bases. All right, we're going to need an acid here because we don't have any dilute acid. We'll just have that sulfuric acid playing the role. And under these acidic conditions, what do we use as our base? Water. If you use the hydrogen sulfate, it wouldn't be the worst thing in the world, but truthfully, water is going to be present. We'll see it get created in our reaction, and that's going to be the stronger base. Okay. The last thing I'm going to do before I have you all try to predict this mechanism on your own is I'm going to tell you that the first step here involves our alcohol that will eventually be playing the role of the electrophile. All right, but we can't kick off that hydroxide group, that crappy leaving group. First of all, it's a bad leaving group. Second of all, we're under acidic conditions, so we can't have hydroxide form in our mechanism anyway. All right, so what's this strategy that we've been using to get rid of that hydroxyl group, to turn it into a better leaving group, specifically under these acidic conditions? We can't substitute it. All right, well, if we could, I mean, we are kind of going to, but the whole point being is that we need to turn it into a good leaving group first. All right, so I'm not going to do like turn it into an alkyl halide or anything like that. That would certainly be a way that I could go about doing this, but there's an even easier way under acidic conditions is to simply protonate that oxygen. All right, then it wouldn't leave as hydroxide, it would leave as that neutral water. All right, so in this first step here, what we've done is we've protonated our alcohol, effectively turning that into a good leaving group. And again, this is the one that's going to be playing the role of the electrophile. And in the next step in our mechanism, we're going to see our other neutral alcohol molecule playing the role of the nucleophile. All right, I will tell you that there are two more steps in this mechanism in order to get to our symmetric ether product. And I want you to take a second and see if you can't reason through what those would be. All right, given these clues that I'm telling you about one playing the role of the electrophile and the other playing the role of the nucleophile, what are my last two steps going to be in order to get to that symmetric ether product? remember, nucleophiles attack electrophiles. So that lone pair on my oxygen is going to attack my electrophile, kicking off that good leaving group. Right? Note that the oxygen itself has that positive charge, but it can't form a new bond because it already has that complete octet. So instead, we're going to kick off that water as a leaving group. And now I'm almost there with my ether. I just still have that hydrogen on there. So in order to get to my ether product, I'm going to have to deprotonate that oxygen. So I'm going to need my water to play the role of the base, leaving us with our ether. All right, so as we said, we have these two molecules of alcohol involved under these acidic conditions. Our first step is to protonate that hydroxyl group, making it a good leaving group. That can now play the role of an electrophile and get attacked by that second alcohol molecule, playing the role of the nucleophile. We get pretty close to being done with just that one step. We just got to deprotonate our ether in order to get our neutral product here. All right, so this is our acid-catalyzed ether synthesis. If instead we wanted to break our ether apart, we could use, again, these acidic conditions. This is now the acidic cleavage of ethers. And we're going to specifically use these hydrohalogen acids. Because not only are they strong acids, but their conjugate bases, those halide ions, are crappy bases, but they are still good nucleophiles. All right, and so what we're going to see in this reaction is we're going to break this ether apart into two chunks. One of them will retain that oxygen and be an alcohol. The other one is going to be converted into an alkyl halide. We're going to, again, look at our reaction mechanism. We're going to note again that we're going to be under acidic conditions. All right, what's our acid in this reaction going to be? Yeah, HBr. We actually won't need anything to play the role of a base. All right, so in my mechanism here, what do we think the first step is going to be? It's the first step that we've seen in a lot of these acidic condition mechanisms. Protonation, all right? And so indeed, we're going to see that our first step is to protonate that ether oxygen. And when we protonate that, we've created this bromide here. We said that bromide is a crappy base, but it is a good nucleophile. And that's my next step here, is nucleophilic attack. And that now neutral leaving group that gets kicked off is our alcohol. All right. Cool. All right. Now let's choose a different substrate here. In this example, we had a symmetric ether. So it wouldn't matter which half we said was our alcohol and which half we said was our alkyl halide. They're the same carbon fragment. But what if we start out with an asymmetric ether? Okay, so the first step in our mechanism would be the exact same. We're again trying to create a good leaving group by protonating that oxygen. All right, but from here, there's kind of these two paths that we could take. Right, we have our protonated oxygen. We have our bromide. All right, but the question is which one of these carbons is my bromide going to attack? Because I would get a different product depending on which one, right? So if it attacked over here, that would give me a mixture of this 1 carbon alkyl halide and this 4 carbon alcohol. Or if I took that same intermediate and that same bromide nucleophile, but instead had it attack the other side, now my product would be a 1 carbon alcohol and a 4 carbon alkyl halide. All right, and I will tell you that you do not get a mixture of both of these here. There's going to be one of these pathways is far more favorable than the other one. All right, who's got a guess here of which one is going to be the more favorable pathway, the one on the top or the one on the bottom? Why the one on the, it is the one on the top. Why the one on the top?
More accessible.
More accessible, absolutely, right? So that bromide, in order for this reaction to occur, it has to be able to access that carbon. Well, this single carbon over here is far more accessible than this very crowded tertiary carbon over here, right? So this is going to be my preferred pathway here, my actual product that's formed, and we're going to note that that's because the halide attacks that more accessible carbon. All right, it cannot reach this one. Okay, so then let's do a practice problem here. I'm going to give you this asymmetric ether. We're going to treat this thing with HBr. And everybody's going to take a second and tell me what my two products are. All right, so I'm going to look at my ether here, and I'm going to note that my carbon that's bonded to my oxygen on this side is a primary carbon. It's only got one carbon neighbor. On this side, though, it's a secondary carbon. So which one is my halide going to attack? The primary carbon or the secondary carbon? The primary carbon. So that is going to be my halide fragment. All right, just to keep my color coding consistent. That blue carbon will get my halogen. And the alcohol's oxygen will be retained on that larger fragment on that secondary carbon. All right, so with these asymmetric ethers, we have to remember ether decomposition, cleavage will be consistent. That halide attacks that more accessible fragment, more accessible carbon. All right, we'll pick up with this next class period. We got one more reaction that we can use to create ethers, specifically how to create an asymmetric ether like this one. We're going to end things now.